Hey, John here. Let's talk about how to call subroutines on a RISC-V machine, all right? That's governed in what we call the ABI, or the Application Binary Interface, which is just another way of saying, how are you supposed to use all the registers in the machine, okay? Now, I'm going to use this document here. There's a copy of this on GitHub. I'll put a link to it in the description below this video, which is right here, but I'll put it in the description so you can click on it and grab a copy if you want. The diagram I want to look at right now is near the end of chapter 5 here. It's this table right here. It's in this section right here that's called CPU registers, which just describes the conventions for using each one of the registers, okay? We know we have 32 registers, okay? They're called X0 through X31. Some of these registers are used as just scratch areas, other ones are used to hold parameters that are passed to subroutines and so on. This table down here describes what each one of them is for, which role each one plays, all right? Register 0, X0, always has the value 0 in it no matter what. It is hardwired to 0. It is welded to 0. Anytime you read the contents of X0, it will be equal to 0 no matter what, okay? Also, if you ever store anything into register X0, it will be discarded. You can never change the contents of X0, all right? Always going to be equal to 0. Register X1 will hold the return address, okay? Whenever you call a subroutine, before you call it, you want to put the return address of what the subroutine is supposed to do. Where is it supposed to go when it's done, right? That's stored in this return address register, okay, which is X1. Now, notice it says register alias description, okay? The alias here can also be used. If you write an assembly language program, you can say things like, load register X1 with something and, add to it or whatever. You can refer to it as X1. You can also refer to the exact same register as RA if you would like to, okay? These are the role-based names or an alias for the same thing, all right? So these are equivalent. So sometimes you'll see people writing programs referring to RA and SP and so on. Other times you'll see them referring to X1, X2, and X3, all right? So keep it straight in your head. They have two different names. Sorry about that, but that's just the way this thing goes, all right? The aliases here, the role-based names are other than X0, okay, which is welded to 0 no matter what. These are just by convention. These are recommendations. We don't have to follow the recommendations if we don't want to. However, if you ever want to call a subroutine that was written by somebody else and put it into a library, a standard library of some kind, you need to follow these conventions. Otherwise, all the registers will get corrupted and stuff like that, right? It just makes sense. You have to agree on the fact that register 1 over here is going to hold the address to return to after a subroutine's done. It's as simple. It's as plain and simple as that, right? Register 2 will be used as the stack pointer. All right, RISC-V uses a full descending stack, and the register 2 is going to be used as the stack pointer while your program runs. Now, the GP and the TP are a little bit more advanced. There's some subtle things about these, but in the simplest of terms, the global pointer is essentially used to access the data region in the BSS of the running code. The thread pointer is used for what's called thread local storage. It's beyond the scope of this particular discussion. We'll have to talk about this at another time. All right, but it works very much like the global pointer, right? If you're familiar with multi-threaded programming, this is the base register for your thread local storage. So what are these T0, 1, and 2 temporary? Okay, what these are used for is when you're writing code in a subroutine, if you need to use registers to hold values, you can store them in X5, 6, and 7, and you don't have to restore their original values when you return from your subroutine, okay? These are allowed to be clobbered. You call a subroutine, and when it comes back, you cannot count on these registers of having any values in them that you had before you called. Now, providing this as a convention allows subroutines to be able to use, registers and do stuff without having to store things in memory and reload them back. I mean, this machine has 32 registers. A couple of them can be used as scratch, all right? You'll notice that the temporary 0, 1, and 2 are in registers 5, 6, and 7. Temporaries 3, 4, 5, and 6 are way down here, and registers 28 through 31. All right, now you'll notice that the saved registers and some of these other are in two groups as well. The reason they're in two groups is because there is versions of the RISC-V that only has half the registers in it. All right, so in other words, these registers 16 through 31 are not present in the smaller embedded version of the RISC-V. Okay, so they wanted to give that CPU a chance to have some temporaries, some save registers, and some argument registers. All right, and the bigger one simply then has more saved and more temporary. Okay, so this is because the smaller ones cannot access these larger register numbers. All right, so they're in two groups. Yes, so the temporaries are not saved by subroutines. Okay. What's S0 and S1? These are saved. If you're in a subroutine and you used all your temporary registers, you need to use more registers for your local, working variables and things, and you decide, I want to use registers 8 and 9. Well, you need to save those because before you return from your subroutine, you need to restore these back to what they had before. Okay? So you get temporary, you can clobber them, don't worry about it. Saved, you need to save them in the subroutine. That's why it says yes over here before you return to a caller. All right. What are these things? Well, there's an optimization in RISC-V that some other CPUs don't have. And that is that rather than storing all the arguments to a subroutine in an activation record on a stack, the RISC-V can store the first 8 arguments in these registers here and just call a subroutine. Plus, arguments 0 and 1 can be reused when the subroutine is done to hold the return value. Okay, now why are there 2? Well, that gets into things like, let's have a 32-bit machine like an RV32i, and it wants to return a value of a uint64t. Well, that needs, twice as many bytes as I can fit into a register. So you can put half of it in each one of these 2 registers, all right? And there's some rules about when to use which one for what types of values, all right? The short of it is A0 through A7 hold the first 8 arguments that you can store in these registers and pass them into a subroutine, as well as return value if it fits in these 2 registers. If you need more space than this, then what happens is you need to spill the rest of them into the stack like you would on other processors, right? Like a Pentium machine or a 68K or something like that. It might push a bunch of arguments into the stack before it calls a subroutine. Okay. So in the simple case, everything runs faster if you just never touch memory. That's why they said let's just put the first 8 in these regs. These are more of the saved registers we just talked about, and here's, as you know, the more of the temporary registers that we were already talking about, right? So you got plenty of temporary registers. You got 7 temporaries, plus notice that the arguments are not saved either. You can use all these as temporary registers as well. You can clobber them before you return from your subroutine. All right? So what does this then all mean? How do we now take advantage of this and the instructions that we've already looked at, combine all this into one big picture? How do I write a program that uses this thing? So what we're going to say here applies to basically the entire RISC-V family here, all right? The ABI for the whole RISC-V family. I'm going to focus, however, specifically on the RV32i in this particular discussion, all right? But like I said, 99% of this applies to all the other modes as well, all right? 64-bit, 128-bit, and so on, all right? So we know we have the 32 registers. What are we going to do with them? Well, guess what? The stack pointer points to the bottom of a full descending stack right here, okay? The global pointer, like I said, it's going to point down here into the data in the BSS, all right? Now keep in mind that the RISC-V only has load, like byte, load half word, load word, and it has store byte, store half word, store word. These are the only instructions that can read from memory and that can write to memory. That's it. There's no other way to touch anything in the memory, all right? All the loads, all the stores have a similar kind of a format, okay? In that the address that you're storing into or loading out of always looks sort of like this, IMM, off of some register. And this immediate value can have a range from minus 20, like 2048 up to 2047. All right, in hex, that's hex 800. Right, that's negative 2k, we say, and then that, and 2047 is hex 7ff, and you can sort of see here that there's a sign bit on here and that's not on over there. Okay, this is the largest negative number, that's the largest positive number, okay, for this immediate offset on this register. Okay, so what does that really then mean? Okay, well, if I want to use these instructions to load and store values from the data in the BSS region, and if I point this global pointer here, remember I said the global pointer is going to be used as like a base register, so that we can use it in here in the various instructions that have an address expressed this way. If you put the GP register in there and the offsets work like this, then, you know, half of the offset values are in this text region down here. And the other half come up and can refer into the data in the BSS. So that's not, right, you know, the most optimal way to do this. So what we're going to do is we're going to store the global pointer register into the data region here. Okay, let's call this the start of the data region. Okay, let's call that one data start. Plus, no, I put an extra 0 in here so I can show you that when I'm adding, I'm not adding a negative value here, right? So the global pointer is going to be hexadecimal, 0800 beyond the beginning of the start of the data region. Now what happens is if I say hexadecimal 800 for my displacement off of my register value, what I'm really doing is subtracting that hex 800, and that would refer to the first byte in the data region, okay? If I said 0 off of the global pointer, I would be referring to this 800 in hex into the data region, and I can then move all the way up to 7FF off of the global pointer, and that would move up into the BSS region in this particular example. So it lets me reach up and down, okay? And this range here is 4K, we say. I'll put quotes around that because it's really 4096 in decimal, right? But in hex, what that number is 1 with 3 zeros after it, okay? So this gives us a 4K region that we can access off of the GP register. If you need more, if I want to reach way up here beyond this 4K, I mean, 4K doesn't sound like a lot these days, right? What if it's a megabyte into there? Well, what you do is you can calculate 1 million and store 1 million into another register and then add that to the GP register and then create a new base register that points up here, 1 megabyte beyond the end of GP, all right? That's how you would then access things up in here if you wanted to do it that way, right? Or maybe your data in the BSS are really big and you need that sort of thing, okay? So this is the theme that we use to get around in the memory when we don't have the ability to say, 1 megabyte off of the GP register and just reach up there direct, okay? We just use the add instructions and other ones in order to calculate a new value, okay? All right, so let's look at what do we do to call a subroutine now? Well, we know we need to put the arguments into register A0, A1, and A2, and so on. So let's write a little subroutine down here. Let's call this one, sub. RTN. All right. Now in RISC-V assembler, what you do is you put a label and you put a colon after it in order to let the assembler know that that's a label and not something else. All right. This is very common in a lot of assembly languages. Let's say, what are we going to do in here? What we're going to do is we're going to write a subroutine that does this. Let's say in C, it would do this. Return like, argument 0 plus argument 1. Okay? Semicolon. How would we do that? Well, we know that the arguments come in the registers called A0 and A1 up to A7 if you have that many arguments. So what we need to do is calculate this sum and store it in the register that we want to use to return a value. Remember, the return value is in A0 in this case, all right? So let's see how that's then done, all right? So if someone calls this, and we'll write the code to do that up here in a minute, we need to calculate this sum, put the sum in A0. That's easy enough. You just simply say add A0. Remember, this is the destination register and the add instruction. And then we say A0. This is RS1. And then plus A1, right? Because in RISC-V, we could say, register 1 equals the sum of register 2 plus register 3. It's a 3-address machine. We can have 3 separate operands in a lot of these instructions. That's the point, okay? In this case, we don't need all 3, so we just simply say A0 plus A1 and store the sum in A0, okay? Now, what do we do to get out of here? To get back to the caller, we need to go to the address that's stored in the return address register, okay? So how do you do that? There's no go to the value in a register, but there is an instruction called JALR, J-A-L-R, jump and link register. And we know what that does. It takes an RD register and it takes an immediate offset and an RS1 register over here. It's going to add this immediate offset to the contents stored in this register. It's going to use that address as a target, and it'll load that into the program counter. So this is essentially go to the address that's expressed by this expression over here. And in the process of getting there, store the address of the next instruction down here, right, into the register that we specify over here. Okay? Well, we don't want to wreck registers. We're not calling a subroutine. We're trying to return from one. So we don't care about this down here, right? So remember what I said about register 0. If we put X0 in here, what we're doing is we're telling the JALR instruction not to bother storing its return instruction address anywhere, okay? Throw it away. Put it in X0. Toss it. We know where we want to go is in the RA register, because it was the responsibility of whatever subroutine calls this to put it in there, okay? And that's where we want to go. So we can say go to 0 off of the value in the return address register. So this thing defeats 2 of the 3 fields in this instruction, but it effectively just simply says go to the address given in the RA register, okay? We don't care that we don't want to go to RA plus 4 or some other thing. We want to just go to RA, and we don't care about the address that could be used to hold the address of the next instruction down here, all right? So this is your entire subroutine that does this, all right? Boom. You'll notice we never touched any memory. This runs much faster than a subroutine that needs to touch memory, okay? Now, how do we get here, all right? So let's say here's my program up here. Maybe, let's call this program. Some other label up here. What's going to happen up here? Well, it's going to do whatever it's going to do, right? And then in order to call this, it has to get some value into A0 and A1 before it comes down here. So it might do something like this. Let's say, I'm going to put a comment over here. Let's say we want to set A0 to the number 10 in decimal, okay? And we want to set A1, A1 equals, 23 in decimal. All right? Then we want to say call, and I'm going to put quotes around this because that's what we're going to try and do, call subroutine. Okay, when we're done, we're going to just stop. I'll put quotes around that too. And the way you stop this thing is you just put an e-break instruction in here. All right, the e-break instruction on RISC-V is reserved for calling operating system features and services and or to tell a simulation environment to halt the processing of a program. All right, so we're going to do this. We're going to call a subroutine. When the subroutine's done, it's going to come back up and we're going to halt. Okay, so how do you get 10 into a 0 register? All right, there's like no load immediate instruction. All right, now how do you do this? Well, what you can do is you can say add immediate destination register of A0. And what we're going to do is, remember, the way this is formed is a lot like this. You got this immediate offset, and then you've got like a base register in here. Well, what if we add 10 to the contents of register 0? Right? That's 10, and it'll put it into A0. That's how you just simply get 10 into A0. And the next thing, we do the same sort of a thing for the 23. A1 is 23 off of X0. Okay, or you can actually put the entire word 0 in here if you want to. That's the role-based name for X0 if you would want. All right. Now, how do you get down here to this subroutine? Well, we need to put RA has to equal the address of this instruction here so we can get back to where we need to go, right, after this instruction is done with the subroutine, right? And we need to also load the program counter with the address of this label down here, all right? Now, there's another instruction just like jail or jail that is designed for this purpose, okay? So how does this thing work? Well, we say jail, we then say RA, because this is going to be the address of the next instruction is going to go into this destination register based on the definition of what jail does, okay? This takes care of getting the return address set up, okay? What about this target address over here? Now, the way jail works, the way the assembler works, so you just simply put the name of the subroutine in here, okay? Now, what that means is, to the assembler, it calculates the distance from this instruction to this subroutine. Because remember, this is program counter relative addressing. If it was to do this, it would need to know inside the encoding of the jail instruction this PCREL value that goes over here. It's not the address of subroutine. It's the distance between the address of the jail and the address of the subroutine. Now, as written right here, we know the address of jail. Let's call that address X. If this is exactly the source code of your program, and jail is at address X, we know for a fact that e-break is at X plus 4. And therefore, and if nothing else is in here, we know this must be at X plus 8. Okay? So it turns out the value in here in the source code is a label or, the address you want to go to. But the address that's stored in the immediate value in this instruction is going to be that 8 right there, because that's the distance that it needs to go to get there from where it is. Okay? So this basically is your whole program at this point. We don't even need any memory. We're not even using the stack. This machine is so simple, and this example is so simple that whenever you have subroutines that only have from 0 to 8 arguments, you can get in and back out without ever touching any memory, in theory, right? Depending on what you need to do in your subroutine, right? So this is the simplest example of how to call a subroutine and how to get back to where you came from. Now let's look at one other example. Let's say we have a more complicated subroutine. So in C, let's say I have some function f, right, that maybe it takes an int I, and then inside here maybe we have a couple of variables, and let's say we have an array, right, int a, and we have like 20, okay, and then we go on to do our various code down here. Okay. where does this go? Okay. Well, if you need 20 integers, you don't really have enough registers to hold all of them. Or let's say this is 100, all right? You certainly don't have enough registers to hold 100 no matter what happens, okay? Where do they go and how does this thing work? Well, now what happens is when you enter into this subroutine F in assembly language, it's going to do something like this. The 100 integers, how many bytes of memory does that need? It needs 400 bytes, right? So this whole thing is 400 bytes. So what's this thing going to do? Well, remember, we use the stack for this. We need to put those 400 bytes in the stack. So what we need to do, it's a descending stack. We need to bop that down 400 to make a hole to store our array elements in there, okay? So what are we going to do? We're going to say add immediate, stack pointer, what? Minus 400 off of a stack pointer, okay? Take stack pointer, subtract 400, store the results in stack pointer. Done. Now, if I wanted to say something like a sub, 2 equals 3, how would I do that, right? And when this thing is compiled, it'll say, well, I know that a sub 2 is where? That's 2 times the size of this integer here, right? So that's the 8 bytes in, right? So if you look at the memory, what do we got here? We got one A0 there, A1 is here, and A2 is there. 1, 2. Each one of these is 4 bytes long. So if we just move down the stack pointer to make a hole, and the stack pointer is pointing, basically, it would be pointing right there. Well, A sub 2 is 8 in to the stack at this point, right? So if you wanted to set A2 to 3, what we would do is we would simply say, first of all, we got to get 3 into a register so we can store it, right? So you might say add immediate, temp 0, 3 off of X0 to get the 3 into register T0, right? Then we might say then store word temp 0, what? 8 off of the stack pointer, okay? Done. So we just got into this subroutine. We allocated enough space to hold this array. The array is not initialized, so it's garbage. That's fine. We just made a space for it and left it. Whatever is there is in there. And then we calculate the value 3 and store it in a register. And then we poke that into the stack where it belongs. So this now will have put a 3 right in there. All right? And, it can go on his merry way and do other things when he's all done. What does he do? He's going to say jailer, right? X0, 0 off of RA to go back to the caller. Now, of course, before you do this, you got to remember, add immediate stack pointer, positive 400 off a stack pointer, right? This, you got to restore the stack. Exclamation point. When you're done, you put the stack pointer back where you found it. Go on your merry way. Back to where the RA register says to go. So you get yourself a nice example of a nice simple subroutine that doesn't need any memory to do its job. Come in, do your work, go back. Here's another kind of subroutine. Maybe you need extra memory. Make a hole on the stack, use it, do what you're going to do, restore the stack, go back where you came from. That's pretty much all there really is, all right? Everything else is just compound, more of the same, more of the same. So, thanks for watching. See you next time.